NASA's Perseverance rover, which landed in the Jezero Crater on February 18, 2021, has been hard at work collecting Mars samples, and so far it has collected 11 scientifically compelling rock core samples along with one atmospheric sample. Now, NASA is devising a plan to get those samples and more back on Earth. The space agency has taken to its blog to reveal its updated plan for retrieving the Mars samples, and according to NASA, it's coming to the end of its conceptual design phase. So, how is NASA going to bring back rock samples from Mars? Let's find out. Welcome to Space World. In today's video, we are going to talk about how NASA's sample return mission from Mars will inspire the whole world in 2033. So, if you want to know more about it, then stay with us until the end of the video. In just over a decade, a small capsule shaped like a flying saucer will blaze in from space and smash into an empty Utah desert. Inside the capsule, protected by shock absorbers, will be a precious payload, about half a kilogram of rocks gathered on Mars. After years as a dream, Mars Sample Return, MSR, is now a $7 billion plan, devised jointly by NASA and the European Space Agency, ESA, involving 3 heavy rocket launches from Earth, 2 rovers, the first ever rocket launch from another planet, and a daring rendezvous between the sample container and a spacecraft that would ferry it back to Earth. It's as complicated as sending humans to the moon, says Brian Muirhead, lead MSR planner at NASA's Jet Propulsion Laboratory in Pasadena, California. If successful, MSR would fulfill what a 2011 report from the National Academies of Sciences, Engineering, and Medicine said was NASA's top priority in the study of the solar system. Rovers like Curiosity, the car-sized robot now exploring Mars, are increasingly capable, but their mobile labs are no match for tools available on Earth. So, like the Apollo moon rocks, Mars samples would be valuable across generations, as studies could reveal how a warm and wet Mars became cold and dry. Scientists could also get lucky and find evidence of life. This has got to be one of the greatest missions of space exploration, says space scientist Andrew Coates of University College London. The first stage of MSR is nearly complete and mostly paid for. NASA's $2.5 billion Mars 2020 rover. After its launch in July 2020, the rover landed in Jezero Crater near a fossilized river delta nearly 4 billion years old. Since then, the rover has been widely performing science experiments and occasionally drilling small cores of mudstone and other rocks that could hold signs of ancient life. Each sample containing up to 20 grams of rock and grit has been stored by the rover in a tube about the size of a penlight. NASA is likely to cache some tubes on the ground and keep others on the rover. Now, MSR's next leg would come in 2028, when another NASA lander arrives carrying both a return rocket and an ESA-built Fetch rover. After launch in 2026, the lander would take a slow, elongated route to Mars, allowing it to deliver a hefty 2,100 kilogram payload, more than the Curiosity and Mars 2020 rovers combined. It would touch down in August 2028, after Mars's dust storm season, most likely using retro rockets guided by a new technology called terrain relative navigation. While descending, the lander will use a belly-mounted camera to take stock of the terrain and avoid hazards, putting it within 10 kilometers of the cached samples. After that, the Fetch rover, about the size of a coffee table, will trundle out of the lander to seek the sample tubes deposited years earlier. The rover will rely on solar power, which gives it roughly 6 months to get its work done before it succumbs to the waning winter sun. To meet that tight schedule, it will have to travel up to 200 meters per day, navigating autonomously. It's the only way to achieve the distances we need, says Sanjay Vijendran, ESA's campaign lead for the MSR in Noordwijk. Once the Fetch rover returns to the lander, an ESA-built robotic arm will remove the sample tubes from racks on the rover and place up to 30 of them containing just over half a kilogram of Martian rock and soil in a sphere the size of a basketball. By that time, the 2020 rover will have 43 sample tubes, but some will remain on Mars, so the rocket can remain a reasonable size, Muirhead says. Scientists seem to be able to live with this constraint, he says. the general consensus was, bring us back 30 good tubes and we'll be happy. However, getting the sample sphere off the planet won't be easy, says Angie Jackman, an engineer who is leading the return rocket's development at NASA's Marshall Space Flight Center in Huntsville, Alabama. This will be the first rocket off another planet, she says. NASA knew the rocket would have to be short and stubby to fit in the lander's protective entry shell. It also needed to survive for months in the cold. For years, the agency pursued a hybrid rocket fueled by paraffin wax and a liquid oxidizer. But the selection of Jezero, which has a mild climate for Mars, meant a conventional solid rocket less than 3 meters tall could do the job without fear of its fuel cracking or exploding. The sample sphere will be fired into an orbit higher than 300 kilometers to meet ESA's Earth return orbiter, which is supposed to follow the lander to Mars. With no Martian versions of GPS to guide it, ESA's orbiter will use cameras to track and capture the sphere. The way we've set the geometry, we have a very good chance of seeing it within the first few hours, Weirhead says. After the rendezvous, NASA-built robotic mechanisms will shunt the sphere into a containment module, seal it, and sterilize it. Like a Russian nesting doll, the module will be placed within a third protective shell, and then finally a fourth vessel, a disc-shaped vehicle to withstand a fiery, parachuteless re-entry through Earth's atmosphere. To minimize the amount of fuel needed to send the craft back to Earth, ESA will mostly rely on ion thrusters, which use electricity from solar panels to drive a stream of ions out of the spacecraft, producing a gentle impulse that can be sustained for months. The approach, which ESA's Bepi-Colombo probe is using to get to Mercury, generates so little thrust that each leg of the journey will take 2 years instead of the usual 9 months or so. It's a disadvantage, but it means that we can do this within Europe's launch capability, Vijendran says. So, once the samples arrive on Earth, they'll be handled with care. They will be quarantined in a facility meant to protect the rocks from exposure to microbes on Earth, and earthly life from any Martian pathogens. Developing instruments that won't contaminate the samples will be a challenge, but a manageable one, Meyer says. Now, exactly how scientists will study the samples more than a decade from now is hard to predict, but they will surely want to check for signs of past or present life. Last year, the Curiosity rover identified 2 sites flush with complex organic macromolecules that resemble the goopy building blocks of oil on Earth. But its instruments cannot tease out whether life or geology produced these molecules. With just a few grams of material, however, scientists on Earth will be able to analyze carbon isotopes in similar materials from Jezero Crater to determine whether life created them, says Maria Paz Zorano of the Center for Astrobiology in Madrid, who helped define MSR science priorities and sample selection for an international panel. And if Jezero's clays show no signs of past life, scientists will want to know why. Was it because it wasn't habitable, or because life couldn't get started, asks Benjamin Weiss, a planetary scientist at the Massachusetts Institute of Technology in Cambridge. And this is it for today, guys. What are your thoughts on today's video? Share your views with us in the comments below. Also, don't forget to give this video a thumbs up, subscribe to the channel, and ring the bell icon for more amazing videos about space. And thank you for watching.